Okay, here we go. We are back with more applications of derivatives. So this one looks similar to what we've seen before. Now, we know that on a graph, the slope is given by derivatives. So that's the whole purpose. So on this one, if we're looking for a local maximum and a local minimum, remember, local is the opposite of local is global or extreme. So local's just the ones we're looking at. So our local max is going to be right here. It's going to be the highest mountain. So we're going to call that x equals 3. In our local minimums, we can have multiple minimums. And we've got one here at x equals 1 and one here at x equals 4. So x equals 1 and x equals 4. Okay, our intervals of positive slope. So positive slope is when the graph is increasing. So I'm going to start here on the left. This whole area is decreasing. But notice at the minimum, it's going to turn and start increasing to our next maximum. So the key to this is that intervals of increasing and decreasing change at maximum and minimums. That's worth remembering. This is decreasing, and then we're going to go back to increasing. Why increasing? So our positive slope, this is going to happen at two places. It's happening in between, on an interval between 1 and 3. And then again on the interval from 4 to positive infinity. All right, the areas of negative slope are the exact opposite spots. So as it's coming into that 1, so remember this arrow represents negative infinity. So negative infinity to 1, it's decreasing. And then it's decreasing again here between 3 and 4. So between 3 and 4. All right, our x-intercepts are obviously where it crosses. We know that, from like grade 9. So we've got x-intercepts at half and another x-intercept at 2. Our y-intercept, of course, is, right there. We'll call that 2.5. So 0, 2.5. And then our coordinate, where our m tan is 0. So remember, m tan is the slope of the tangent line, and a slope, remember our friend slope dude? Where is tangent a slope 0? A slope is 0 right here. So slopes are 0 at maxes and mins, which is good to know. So therefore, we have a coordinate for m tan being 0 in 3 different places. So those places are going to be at all of our max and mins. There's 3 of them. In this case, we're going to do our best to write that in. So we're going to say 1, negative 1. We'll call that 3, 1, close enough. And then 4, half. So if I were to draw a slope there, I would end up with tangent lines that were horizontal, which means they have a slope of 0. Okay, find the number of units that produce the maximum revenue for boat business where r equals 800x minus 0.1x squared when r is revenue in dollars and x is the number of units sold. So these x's are how many boats we've sold, and r is going to be our revenue. So maximum revenue, the key to this problem is the word maximum. What did we just talk about having maximums? We know that when a max or a minimum happens, what is the slope? The slope is 0, right? Because it's a maximum. So a lot of times in these problems, it'll talk about rate of change, and that's how you know to take the derivative. But if you're looking for a max or a min, you can also use the derivative for that and set it equal to 0. So we're going to take r, and we're going to find r prime. So r prime of x is going to be 800 minus 0.1 times 2, so 0.2 x. Now if we set that equal to 0, and again, we're setting that equal to 0 because we know that max and mins happen when the slope is 0. So we're going to solve for x. We're going to get negative 800 equals negative 0.2x. Divide out our negative 0.2. And what do we get? We're going to get 4,000. So 4,000 equals x. So that means we need to sell 4,000 boats to maximize our revenue. So that's a new way of looking at things. Okay, if water is being drained from a swimming pool and V of T liters is the volume of water, so our volume is going to be represented by V of T, of water in the pool at T minutes after draining starts, where V of T equals 250 times 1600 minus 80T plus 2T squared, or T squared. Find how fast the water is flowing out of the pool after 5 minutes. So what does the term flowing mean? That's how fast things are changing, right? I don't care how much water is in the pool. I want to know how fast it's flowing. So this tells me, this is another way of saying that we need the derivative, okay? Because flowing is talking about change, and rate of change is derivatives. Okay, so there's a couple of ways we can do this here. We can either use product law, which sounds like a terrible plan, or we can rewrite V of T. And so if we distribute that 215 in, we're going to get, let's see, 400,000 minus 80 times 250 is 20,000. 20,000 T plus 250 T squared. Okay, so that's not my derivative. I just distributed the 250. If we take the derivative here, V prime of T, we're going to get minus 20,000 plus 500 T, right? All right, so this is the derivative, which is going to tell us about how fast water is flowing. Find out how fast the water is flowing out of the pool after 5 minutes. So we're going to put the 5 in. So we're going to find V prime of 5. That's going to be minus 20,000 plus 500 times 5. Well, what is 500 times 5? 2,500. So negative 20,000 plus 2,500 is going to be what? What kind of number are we going to get here? It's going to be a negative number. This is, I think, finally the first time we're getting a negative number. So that means we're losing. The negative is telling us that we're decreasing, right? So we're losing water. So the water's flowing out, so it's negative. And the water's flowing out at, I guess, 17,500 liters per minute. Woo! It seems like a lot of water. Okay, and our last one here, the equation S of R equals 1 over R to the 4th can be used to determine the resistance to blood flow S, so blood flow is S, of a blood vessel that has a radius R in millimeters. Find the resistance at R equals 1.2 millimeters. Okay, so it's asking to find the resistance. This is all about reading. We have to have good reading skills here. The equation S of R can be used to determine resistance. So the original function is resistance. So we're going to need to use just the original function. It's telling us the resistance, and then if we want to find out if that resistance is increasing or decreasing, or the rate of resistance, if that's even measurable, we would use a derivative. So we're just going to plug in here S of 1.2 because we're using our original function, right? And what is 1.2 to the fourth is 2.07. So 1.1 over 2.07. And that gives us about 4.8. 0.48 is our resistance. Now, is that resistance increasing or decreasing? So when we start talking about increasing or decreasing, this is when we're going to look for the derivative. So to find this derivative, if we have S of R is 1 over R to the fourth, isn't it easier to rewrite this as R to the negative fourth? And if we do that, the derivative of S of R is going to be negative 4R to the negative fifth, which is negative 4 over R to the fifth. And we want to know if it's increasing or decreasing at 0.0 or 0.88. So we are going to find S prime of 0.88. And it's going to be negative 4 over 0.88 to the fifth. What a number. To the fifth. And we're going to get negative 7.57. Now the question doesn't ask me what the resistance is. The question is the resistance increasing or decreasing? And because we have this negative number, we know resistance is decreasing. And that will be our answer. Okay, cool. You're geniuses now. Good work.